No, it is not.
It is.
Good. So, welcome to April-May 2020 exam paper. We are going to pick two questions today. Question 1 and question 7. So, question 1. Hey, what does it say?
We can't see you.
Hello?
I'm unable to see you.
You can't see me.
Now I can see you.
Okay, good. And you can see the board behind me.
Yes, it's visible.
Oh, good. Oh, by the way, as you are aware, some of you, you may be aware, 2 weeks ago, I was ordained as a deacon. So
Yes.
we don't just know transformers, we also know the word of God.
Amen.
That's
Anyway,
important.
That's not the discussion for tonight. That's a story for another day. So question 1A, what does it say?
Define a transformer.
How many marks?
Two.
Good.
2
So
marks.
a transformer is an electrical static equipment or I was using the word static electrical gadgets that is used to increase, let me not use the word increase, used to step up or step down AC voltage, alternating voltage. Okay. 2 marks is not much. The keywords are electrical static. Okay. And this step up or step down alternating voltage. That's all. One thing to mention is that, you know, in a transformer, in an ideal, this is not part of the answer, but good to know. In an ideal transformer, TX for transformer, TX is transformer. In an ideal TX, power supplied to a transformer is equal to power delivered, meaning that power is equal to VI. So power at the secondary, at the primary side is equal to power at the secondary side in an ideal transformer, meaning that if that is true, if that is true, it means that V on the primary multiplied by current on the primary is equal to V on the secondary multiplied by current on the secondary. In some books, they will say VP over VS, to bring the VS here, should be equal to IS over IP. Okay? That is in an ideal transformer. We proceed. Part B. Somebody read to me part B of question 1 for April, May 2020. Part B.
Part B.
Yes.
In table form, compare the shell type to the core type transformer.
So we have two types. There is what is known as core type and shell type. Compare core type they have not said include a diagram, but I'll use a diagram because I know the people I'm dealing with. Yeah. Shell type. So, easily remember, shell type, 2 windows. Core type, 1 window. So we are going to have a coil here. This is our V secondary. This is our V primary. That's the core type. Okay. Then in the shell type, the windings are here. This is your V primary. This is your shell type. So, in the shell type, this is your flux, like that. Another flux goes like that. Whilst here, this is how it goes. Okay? But the question said in tabular form, in a table form. So we are supposed to say core and shell. Core, shell. And we are supposed to list the 5 things. Five, like that. The differences. Okay? So, that is only a matter of reading. I'm going to send you the table. Are we together?
Yes.
Is that okay? But I wanted to show you this. But otherwise, I'll send you a table here. Okay? Let us proceed. But see, hello, Patsy.
Yes, sir. Yes, Patsy. Use label diagrams to explain the construction and the operation principle of the transformer.
Use what?
Labeled diagrams.
Okay. Good. So, the label diagram, we are going to use the code type. To explain the principal operation of a transformer. Okay, so that which we have drawn is known as the core. Okay? When you draw this core, then we can actually go to the primary side and put a winding. B primary, voltage on the primary. Okay? So, I will start explaining just here. So, first point, the core of a transformer is constructed from laminations of silicon steel to aid or help or assist the easy movement of magnetic flux from primary side to secondary side. Okay? That is the whole essence of the core. The core is made of silicon steel, which is simply an alloy of iron. And this silicon steel is there to ease the permeability, the movement. Listen, current is to conductivity, as magnetism is to permeability. A material that can easily conduct electricity, we call it a good conductor of electricity. For example, copper and aluminum and silver. A material that can easily conduct magnetism, we say a material has good permeability. A material which can easily conduct electricity, we say it has got low resistance because it has got good conductivity. So current is to conductivity, and the opposition to conductivity is the resistance. Magnetism is to permeability, and the resistance to permeability is called the reluctance.
DDK.
Good. So the other reason is people ask, why do you use copper? Is it because it has got good conductivity or it has low resistance? Why do we use the silicon steel? It is because it has got good permeability or low reluctance. We proceed. So now, after I have supplied the current, you have supplied the voltage here, what is going to happen? Okay? So, where does this magnetic flux come from? Where? How does it start? Okay? We have said this core is there for it to be able, the purpose of the core is for it to allow magnetic flux to pass around it. But where does it come from? Professor Joseph, you're welcome, my son. So, what is the source?
Thank you, sir.
Of this magnetic flux? Okay? And that is your second point. So your first point, in explaining a transformer, you talk about the core. Just talk about it. When you talk about the core, two things. Talk about the material and the purpose. It's sharp. Okay? Don't just talk anyhow. No, what the transform. Be systematic. Okay? Let people know that you have been taught by a professor. Okay? So we go systematically. We can't talk about the transformer without talking about the core. So first thing we talk about the core. And the core is made of silicon steel. Why? To allow easy passage of magnetic flux from where to where? From the primary side to the secondary side. Even in the exam, my spirit will enter and you will be seeing me in the exam. We proceed. So, second point is that when voltage is applied on the primary side. Okay? How is voltage applied? Through the winding. This winding here. When voltage is applied on the secondary side through the winding, what happens? Okay? Magnetic flux is induced in the core. Okay? When voltage is applied on the primary side through the winding, magnetic flux is induced in the core. Then what happens? This magnetic flux will start moving in the core. So we can put here magnetic flux, U. Okay? Magnetic flux. Are we together? Then what happens when this magnetic flux is there? Okay? So here there will be secondary winding. And on the secondary winding, we have the secondary here. So if you want, you can record here primary winding. And then here, you say secondary winding. So now, ladies and gentlemen, you apply voltage here, it induces what? Flux. When this flux meets a secondary winding, what does it do? It induces the voltage in the winding. Another point. The flux induced on the primary winding it then induces voltage on the secondary winding. So what is happening here, gentlemen? On the primary winding, you induce voltage. This voltage induces what? Flux. On the secondary, it is the flux that gives you voltage. So on the primary, you have voltage introducing flux. On the secondary, you have flux introducing voltage. Gentlemen, that marks the end of a transformer. Sometimes we may say, give us the EMF equation of a transformer. But in this question, it was not asked. But I'll give it to you on a bonus. EMF equation of a transformer? Is given by EMF equation is equal to (4.44) frequency 5A. Those are the three things that are important in a transformer. Number one, number of turns on the winding. Number two, magnetic flux. Number three is the frequency. In Zambia, we use 50 Hz. This is the voltage. Now, listen to me. Flux and frequency, these are same on both sides. The flux and the frequency will be the same on the primary or the secondary, because the flux is the one that is moving here, which is actually, it's not even moving. We use the term pulsating. The pulsating flux, which pulsates at the frequency of the voltage supplied. So the frequency and the flux is the same value on the primary and on the secondary. The voltage is dependent on the number of turns. The more the voltage, the more the number of turns. The less the voltage, the less the number of turns. So when we want to step up the transformer, we increase the turns on the secondary. If we want to step up the voltage. If we are stepping down the voltage, we just reduce the number of turns they need to give us that voltage. Gentlemen, this marks the end of the lecture on question 1 for April 2020. I'm running out of time. Meet me in the next 3 minutes as we tackle question 7 for April, May 2020 Teveta exam. Thank you.